In this video, we're going to talk about product and quotient rules and higher order derivatives. So the product and quotient rules, these are ways of finding derivatives of functions that are in a certain form, particularly in the form u times v, where u and v are both functions. And so we want to find the derivative of that, and also in the form u over v, again, where u and v are functions. And so the product rule just states that u times v, the derivative of that is equal to the derivative of the first function, u, times v, plus u times v prime. Okay, so there's a lot of different ways of writing this, but I like to use the u's and v's. It's a nice compact way of writing the product rule. Essentially, it's just saying take the derivative of the first function, multiply by the second function, add it to the first function times the derivative of the second function. Now the quotient rule, u over v, taking the derivative of that, is going to be u prime v minus u v prime. All of that is divided by v squared. So we want to find the derivative. We're going to look at an example here. We're going to find the derivative of f of x equals x squared times sine of x. Now I'm going to write this out a little bit. I'm going to write more here than I normally would, but we're just going to kind of break this down and make sure that we know exactly how to do this. I'm going to call this first part of here, that's x squared, I'm going to call that u. So I'm going to say, all right, I'll let u equal x squared. And then I can see here that v is equal to sine of x. And I see that if I define u and v that way, then my function f of x is in the form u times v. And so to use the product rule, I'm going to need to find u prime and v prime. And so let's go ahead and see if we can write those down. U prime is equal to 2 times x. And v prime, so the derivative of sine is going to be cosine. All right, so I get cosine x. And I just use my product rule here. The derivative of u times v, just write down my product rule. U prime v plus u v prime. And let's just fill it all in. U prime is 2x. V is sine of x. Plus u, which is x squared. And v prime, which is cosine of x. And it looks like I've got it. At this point, I'm just going to maybe clean it up a little bit. Let's see, that would be 2x sine x plus x squared cosine x. And so we found the derivative. And of course, there's always algebra. There's things that we can do to write these things in different ways. I mean, perhaps this could be written as, let's see, I could factor an x out of here. I could write this as x times 2 sine x plus x cosine x. I'm not sure that's really necessary to write it that way, but especially when you're taking multiple choice exams or questions, you want to make sure that you know that there are different ways of writing things. Recognize that, if you see an answer like this, it's equivalent to this answer right here. Okay. So let's take a look at another example. Here I want to find the derivative of g of t equals 2t plus 7 divided by 3t minus 5. All right, so I'm just going to go, I'm not going to quite write everything out quite as much as I did in that last example. I know I've got a quotient here, and I know that my quotient rule is in the form u prime times v minus u times v prime over v squared. And I know that u here is going to be just the top. That's 2t plus 7. And so u prime, it looks like that would be 2. And I multiply that by v, which is 3t minus 5, minus u, which is 2t plus 7, times v prime, so that would be the derivative of the bottom, which is going to be 3. And all that goes over the denominator squared. Now, don't fall into the trap of thinking you can cancel things out right now. You got a 3t minus 5 up here and a 3t minus 5 down here, but that 3t minus 5 is stuck in this term over here. You can't cancel that with the denominator because, you would need it to be a factor of the whole thing up here. And so you can't just cancel out parts of the numerator with something in the denominator. What we could do, though, is we could do some multiplication. We see if we can simplify this a bit. I want to multiply this 2 inside the parentheses to get 6t minus 10. All right, I'm going to multiply this negative 3 inside the parentheses. So that's going to give me negative 6t minus 21. And all that is over 3t minus 5 quantity squared. And so it looks like, well, my 6t's cancel out. It looks like I'm left with negative 31 in the numerator and 3t minus 5 squared in the denominator. And I found my derivative. Okay, let's look at another example. Here I want to find the derivative of f of t equals tangent of t. All right, now I don't have any rules, at least, nothing that I've mentioned about finding the derivative of tangent. But one thing I do know is, from the trig class, is I know that tangent of t is the same thing as sine of t divided by cosine of t. That's a pretty basic trig identity. And that's a quotient. And so if I want to find the derivative here, even if I don't know it, there's formulas and things out there for the derivative of tangent. You could look that up. But even if I don't know that, if I don't remember what that is, I know this. And I know that's a quotient, and I could use the quotient rule to go in and see if I can find that derivative. So f prime of t is going to be, let's see, u prime times v minus uv prime over v squared. And so the derivative of the top, well, the derivative of sine is cosine. So I get cosine of t. And I multiply that by the bottom, which is cosine of t. Minus the top, which is sine of t, times the derivative of the bottom. So the derivative of cosine. Now remember, the derivative of cosine is negative sine. Okay, and I've got all that. I'm going to divide that by the denominator squared. So that would be cosine squared t. All right. Let's just clean this up a little bit. Let's see, I got cosine times cosine. So that's going to give me cosine squared t up here. I've got a negative and a negative. So when I do all the multiplication here, those are going to become a positive. So that's plus sine squared t. All that goes over cosine squared t. Now we have another trig identity that we can remember. Cosine squared plus sine squared. This is what's called the Pythagorean identity. And cosine squared plus sine squared, that just equals 1. Now if you don't know that, you may need to go back and take a look at the trig identities. Just go back and review those. You should have come across that. If you've taken trig, you certainly should have come across that identity before. And what we got in the bottom is cosine squared. So we found the derivative here. Now I could leave it like that, and that's okay, but if you remember, one other trig identity is that 1 over cosine, that is how we define secant. And so I could rewrite this as secant squared t. And I don't think there's really a whole lot else that we could do with that. Okay, let's look at another example here. Here I want to find the equation of the tangent line to y equals 27 over x squared plus 9 at the point negative 3 3/2. All right, so now let's just remember for a second that to find the equation of a line, we need a couple of things. All right, so I'm not doing any derivatives or anything yet. All I'm just doing is kind of remembering from algebra that to find the equation of a line, we need m, which is the slope, and we need x1, y1, which is just a point on that line. So that's the minimum information that I need to be able to find the equation of a line. And if I have those things, then I can write down the equation of a line. And there's different ways of doing this. I just like to use the point slope formula, which is y minus y1 equals m times x minus x1. Some people like to write down y equals mx plus b, go ahead and plug in the m, and then plug in the x and the y value in place of x and y to figure out what b is, and that's okay too. That's just another way of doing it. But either way, you're going to need the slope and you're going to need the point. Well, I've got the point. I'm told that this point is on the line right here, but I don't have the slope of the tangent line. And so what I need to do is find the slope of the tangent line. If only we had some kind of way of finding slopes of tangent lines. Oh, we do. They're called derivatives. And so what we need to do is find the derivative. I see here that I've got a quotient. And so if I write, I'm going to just write this down again. Y equals 27 over x squared plus 9. And now I need to go ahead and find the derivative of that. So I'm going to call that y prime. And I see this is a quotient, so I know I'm going to use u prime v minus uv prime over v squared. Let's see, the derivative of u, that would be the derivative of the top. Well, hey, we've just got 27 up here. The derivative of that is just 0. And it doesn't matter what I multiply by that, because that's just going to be 0. But just to kind of stick with the formula, u prime was 0, v is x squared plus 9. I'm writing it, but I really know that's just going to cancel out. Minus u, which is the top, that's 27, times v prime. So the derivative of the bottom is 2x. And all of that goes over x squared plus 9 quantity squared. Okay. So, I know that I'm about to plug a number in here. I know I'm about to plug -3 into this thing. And you could just do it right here. But maybe I'll simplify things a little bit first. It's not absolutely necessary. You could just plug the -3 in place of x here and see what you get. But I'm just going to simplify it. This part here is just 0. -27 times 2x is going to give me -54x. That goes over x squared plus 9 squared. Okay, and so I know that the slope is going to be, this thing right here with -3 plugged into it. So the slope would be y prime of -3. So if I stick -3 in here, let's see, -54 times -3 is going to give me 162. -3 in here will give me 9. Remember, if you're squaring a negative, this turns out positive. So -3 squared is 9. Add 9 to that, you get 18. Square 18, I think that's 324. And 162 over 324, well, that's just, let's see, that's just 1/2. Okay, so I've got pretty much everything I need. I know I've got the point, -3, 3/2, and now I know that the slope is 1/2. So if I go in here and I use my formula, y minus y1 equals m times x minus x1, let's plug in all the right stuff. I have y minus 3/2 equals 1/2 times x minus a -3. Okay. Well, looks like I can do a little cleaning up here. That would be y minus 3/2 is equal to 1/2 x. This becomes a positive 3, and multiply by the 1/2, you get a positive 3/2. And so if I drag this across the equal sign, looks like I end up with y equals 1/2 x. 3/2 plus 3/2 is going to give me 3. And I've got the equation of the tangent line now. Okay, so let's talk about higher order derivatives for a minute. All right, so we're going to talk about the derivatives. Now we've been really talking about the first derivative all this time. When we've been doing, just the derivative, f prime. Sometimes we'll write it down as dy dx. So this is called the Lagrange notation. This is called the Leibniz notation. Both of them just mean the same thing. It's just the derivative. But we could go on to find a second derivative. And the second derivative would just be, hey, you start off with the original function. You take the first derivative and you get here. The second derivative would just be to take the derivative of that thing and to get down to here. So we just take the derivative twice. And the Lagrange notation is just going to be, f double prime. The Leibniz notation is going to be d squared y over dx squared. And really that's just a shortcut way of writing this right here. If you go in here, let's ignore this part of it, and you just have a df dx, so that's just the first derivative. And then we take the derivative of that again, so we get a d dx of that. Then all we're really doing here is we're just sort of, making a little shortcut of that formula. Third derivative, f triple prime, d cubed y over dx cubed. So we just have, these are just the notation for writing that. And so it's a pretty straightforward thing here to find higher order derivatives. And don't worry so much about what does this mean when we find higher order derivatives. We'll get into that at some point. But let's just see how to do it first. Here I want to find the third derivative of f of x, where f of x is defined this way. Well, it turns out that if you have polynomials, then this is actually pretty straightforward. The first derivative, let's see, that would be, the 4 is going to come out in front, so we get negative 8x cubed plus 3x squared minus 10x. And that would give me a negative 4. Okay, so I'm just using my differentiation rules there. The second derivative would be the derivative of this one. All right, so you start with the original function is this. The first derivative is the derivative of this. The second derivative would be finding the derivative again. So it looks like we get negative 24x squared plus 6x minus 10. And then the third derivative would be the derivative of the second derivative. So that would be negative 48x plus 6. So let's talk for a minute about what these higher order derivatives mean. One example is right here. So if you start off with a function that tells you about position, think about, I don't know, like maybe driving a car. So if you have a starting place and then you're driving a car, you may have a function that tells you the position of that car at any given time. Well, if you take the derivative of that, then what you're talking about is velocity, because remember, the derivative is the instantaneous rate of change. And so the rate at which the position changes with respect to time is what we call velocity. If you take the absolute value of that, you're talking about speed. Well, if you take the derivative of that, then you're getting acceleration. That's the rate at which the velocity is changing. Think about if you're driving on the highway and then you want to pass somebody, you speed up, right? Your speed changes, and that would be your acceleration. And so velocity is the first derivative of the position function. Acceleration is the derivative of the velocity function, which is the second derivative of the position function. Another way of thinking about higher order derivatives is that sometimes we want to approximate a function near a given point. And so suppose we want to approximate f of x where x is close to 0. Well, higher order derivatives can be used to make this kind of approximation using something called Taylor series. And so Taylor series, now I'm not going to go into where this comes from, but it's a way of approximating a function. And so f of x is approximately equal to f of 0. This is for when we're close to 0. F of 0 plus f prime of 0 times x plus 1 over 2 factorial f double prime of 0 times x squared plus 1 over 3 factorial times f triple prime of 0 times x cubed. And we can keep on going here. The idea here is that any function can be approximated by a polynomial, right? Where you have, x cubes and x squares and x's and things like that. And as long as we can find the derivatives at each one of those points. And so this is one way of we using this is one way in which we use higher order derivatives. And I'll just show you a real quick example of this. Suppose that we want to approximate f of x equals sine of x whenever x is close to 0. Well, we know sine of x is, it's a trig function. It can be a little bit complicated sometimes to work with. But suppose I wanted to approximate that. I didn't want to deal with the trig function. I just wanted to approximate it using something else. Well, then our Taylor series says that f of x is equal to this expression here, where f of x is sine of x. So f of 0 would just be sine of 0. F prime of 0 would be cosine of 0. And so we multiply that by x. 1 over 2 factorial times the second derivative. So if the first derivative is cosine, the second derivative would be negative sine. And then the derivative of that would be negative cosine. And we would just kind of keep on going. Now when we go in here and we evaluate all these things, we end up with sine of x is approximated by x minus 1/6 x cubed. We can see here, I've drawn the graph of sine of x. All right, so that's the continuous one here. And here's y equals x minus 1/6 x cubed, this one right here. Well, that's a pretty good approximation of it. However, it's only good when we're close to the point where x equals 0. And that's what we were doing here, is we were really just approximating this when x is close to 0. And so that's one way that we use higher order derivatives, is to approximate different types of functions. Okay, so in this video, we talked about product and quotient rules, and we talked about higher order derivatives. And so I hope that's been helpful to you.